Hello, I'm Shakthi and my team members are Sreekar and Pawan Kumar. So we have worked on this project where we have overcome the drawbacks of ant colony optimization algorithm and also implement that in an application-based manner where we have implemented it in such a way that we can use this in household wiring systems and how the electrical wirings can be more efficient and the best efficient solution can be brought through this algorithm. So what is ant colony optimization algorithm is that it is inspired from the way ants proceed with the pheromone trails, how they follow and get to their goals or the endpoint, that is the food, and how every other ant follows this best part of solution, how they get more efficient with that. That's how ant colony optimization algorithm also works. So starting from here, we can see the drawbacks, how these algorithms tend to process and how we overcame that. So drawbacks are that we have this tradition in this traditional algorithm that these ant colony optimization algorithm follows, and one of them is MOAQ, multiple object and queue system. It's an algorithm where it requires DM to impose certain ordering in objective function. So basically in this even though there are special cases where arbitrary ordering can be there, but still a specific ordering is required for the proper algorithm, like how it can work specifically and properly. So also it needs certain heuristic function. It's supposed to be domain dependent, and the theory analysis is also difficult, and the probability distribution also changes by every iteration that go through. So for every path that these ants follow, the probability keeps on changing, which makes it tough for anyone. And also the time efficiency, time to converge is like uncertain, and it's not stable, and efficiency is so bad in this. So how did we overcome this? So overcoming part happens like with the MOAQ algorithm. So first we try to replace the MOAQ algorithm with gene algorithm, and we found out that the gene algorithm's certain part, that's the taboo search. So the taboo search is where we implemented in this algorithm, and it gave us so much benefits that we can overcome like two factors mainly. One is that we don't need an MOAQ algorithm, and can be like we don't have to have an arbitrary ordering or a certain ordering in a way to find an objective function. It can be anything, it can be an arbitrary again. That's one of the advantages in this. And the time to converge, again, the time efficiency is so enhanced with this. Because how? Because taboo search from gene algorithm works in such a way that it eliminates the least efficient solutions. So taking from if you take an ant and like 3 ants at least, then we make it like move towards for certain goal or a solution or food, and when out of these 3 ants, one ant is like the highest, like the best, and best in the finding this solution, and like one of the ants is like the least, travels so much distance, it eliminates this pheromone trail at all. It's like it's not necessary. So this path is being like erased and it's removed. And the other advantage in this is also that taboo search also enables us to like it won't allow you to previously visited solutions you have, that you won't go to that. It would cancel the search of the previously visited solutions. So that's like, for example, if ant B has chosen a path and that's not efficient, then it won't allow the other ants to go through that path. So that's a great advantage, and how we overcame that. So getting to the code, how we implemented it. So whatever we define outside, all the defined marks, they tend to be the global parameters or global variables. So mass cities are the number of cities that we're going to use, and maximum distance 100 kilometers, we have assumed that, and maximum field is the total distance that ant takes from one city to all the other cities, and maximum ants has 5, so number of ants we are using going to be 5. Alpha and beta, these are like the main functions, not functions, these are the variables that we require like the most. Like alpha is like a learning step, so one pheromone trail is like the best, how the ants learn to go through this pheromone trail. That's why alpha is required. That's the learning step we call it as. And beta is discount factor. So RHO is evaporation rate. So how the pheromone trails evaporate within a specific time, that's the same way why evaporation rate is, how fast they evaporate. And Q value is the cost factor. Like for this case, in this program, in this application based program, Q value is used to find the cost efficiency, I mean the cost factor basically. So how the wiring connections are being made and length of the wires, and how much distance, and how we calculate the cost of it. That's why Q value is used. Maximum choose and maximum time, obviously. And initial pheromones, it's the starting point where the pheromones is 0 basically. So moving on from the header files, these are the header files that we need, and we have defined match cities that we need also, and structure city type. So this structure can be used like further down, like X and Y, these are like main types where we can define the cities that we need. And structure and type is where you require the AND to, like what type of AND type, AND A or AND B goes to which city and current city of its, and the specificity of each. That's where we have defined it. Current city, COR city is current city, net city, path index. So net city is the city where it goes from the current city to other city, and path index is the way it travels through. And Sabio, as I said, it's the main variable I have used as the one we gonna use it for searching. And path is the path, as I said, path index is the specificity of, like, if there are 4 cities, 0, 1, 2, 3, 4, and that's the index of the city, and the path is like from A to B or B to C, that's the path. And tour length, this is the total distance being required to travel, and we have invoked the constructor here, cities type and cities, and type and ants, and double distance, which is a distance, as I said, for each and every city that they cover. And pheromone, again phero, which is basically the pheromone trails that we're talking about. And best is to figure out the best efficient solution. That's why it is best, and best index is the path they traveled, the best path. So coming to the function init, which is initialization, and here we have integer from, to, and. Basically from and to are used for the for loops, and the ant is basically the one that we are asking to travel, and we use 2 for loops here, and the distances are seeming to be 0 from the row and column matrix in the arrays. And phero, as usual I said, it is used for us to as 0, which is initial pheromone. And again we have this for loop, and we open this for loop again, and we enter the row of cost matrix, and we define the variables that we need here to implement the distance. And we have assumed the if condition here. If it's equal to match cities, we have defined, right, 12 cities at the top, maximum cities as 12, so that match cities. And as we go to one city, the current city, the 2 plus keeps incrementing so that it reaches till the max, right? So that's what this statement is about. And another for loop for the, so from this for loop is where we started the initialization, the tabulation, the tab search, this whole sentence of 78 lines. And restart ans, coming to the end of that function, initialization function, which is init, we have this restart ans, where we have, again, once these ans goes to the one solution, I mean, if from the starting node to the end of the node, you have to come back again to the start node, right? It's like using a double linked list. So we are kind of using a double linked list kind of concept over here. So from the last node to the first node, how we travel is where we use this function restart ans. So we have defined it in such a way that we have given this for loop as ant, and if the tour length, we have already got our best value from there, right? So the tour length is less than best, then we assume that this tour length is supposed to be the best, so we assign this value to the best again. And best index, So the best index is where we the best ant is supposed to be the best index right now. The ant which traveled through this particular solution is the best index here. So this nodal path is the best node path, and we further execute that in for net city how they travel, and the pheromone trails have been left here. And double AND product is the way to calculate Q-val. So this is the formula that we can use to calculate Q-val using the pheromone trails, alpha and beta, and the distance. And the further functions will be explained by my teammates Sreekar and Pawan Kumar respectively.
You were saying, so now we have this function called select next city with an integer argument ant. So we got two for loops here, and ant variable is the path variable. So we define the path for ants in such a way that it starts from current city and hence for the loops to get it to start to move. We have a variable called denom which uses the ant product function, and assert is used in order to eliminate the least possibilities. So in the following statement we check if the ant has reached all cities, and if not, then we again randomize the paths. Following is the stimulate ant function where the whole algorithm's key is there. So it allows us to follow the best path by figuring out the efficient path. The loop checks for the maximum number of ants that uses this path and gets updated to the next city. These statements are being used to know if the distance traveled by the ant is less than its previous best, and updates the path index as this one, and also in getting the length value. It also updates the path of its current city and its path for the next city, and if the path is same as the previous best, then it is asked to keep moving until we get the best path next from any of the ants.
Continuing from where Sreekar left, this is updated this function. This is used after when the least effective solutions are eliminated by the asset macro in the section next city function. Now 2 for loops, again each cities when from and to are not equal, then we update the pheromone not to use by providing the from to as arrays in phero, and RHO the evaporation rate is being reduced, and if phenomenon trails is less than 0, and then we again remove that trail by assigning it to initial pheromone. So to add new pheromone to the best index path, we used to follow the below statements, thereby updating the pheromone trail. To add the best path is where again we open 2 for loops for years, cities, and use the best index that is we have got from all the functions performed and update it as best pheromone trail. So now in our main functions we take Kearney time to be 0 and take inputs, update from users and then the values, and we randomize the time and paths, and we invoke the function and performing all this we end up getting the best path index and the print that and the cost too. Thanks from behalf of 3 of us. Thank you.